Good day. My name is Ana Cecilia Garza. I will present an affordable proposal to address housing shortage and energy deficit in Argentina. This project consists of a social housing model developed for a family of up to 4 members, which we call the Solar Cube. This is the result of teamwork between Arquitectura Rojo and eLab Sustainability and Efficiency. There are two issues that we found in Argentina related to residential sector. First, there is a residential deficit of approximately 3.5 million houses. And second, between 2005 and 2017, the demand for residential electricity grew by 86%, twice the growth of the total electricity demand. This data tells us that there is a need of building houses, but also the importance of making them energy efficient. The climatic zone selected for the location of the project is the Pampas region, which accounts for 66% of the country's population. It was essential to start with a precise climate analysis, which allowed us to choose the most effective strategies to achieve an efficient house design. This 3D graphic shows the average temperatures of every month, hour per hour. We can appreciate a clear differentiation of the 4 seasons of the year. In summer, there are hot afternoons and comfortable nights, while in winter, temperatures are constantly below 20 degrees Celsius. And the intermediate seasons have comfortable afternoons and cold nights. In the psychometric chart, we can see in green the comfort zone hours, and in gray the hours where there is a balance between the external weather and the internal gains. First, thanks to the natural ventilation, we increase the hours of comfort inside the house. Then, we chose the main passive strategies to address the hot and cold hours, focusing on the management of solar gains. We decided to base the proposal on solar energy, since it is the main and only external source of energy on Earth, and its path is 100% predictable. The south and east facades receive few radiation throughout the year. Therefore, these walls are opaque and more insulated. The facades that receive the highest radiation are west and horizontal, so strategies to protect them from solar radiation must be implemented. For this, a tension substructure with a climbing plant was proposed in the west facade and a vented over roof for the horizontal facade. The radiation received in the north facade is concentrated in winter, precisely when heating is necessary, so it is an opportunity to take advantage of solar gains. Also, windows with horizontal louvers were designed in this facade. The horizontal louvers were calculated by analyzing the sun path throughout the year and defining the design angle, in this case 65 degrees, to allow solar radiation during winter but protect from it during summer. Here we can observe how the facades that receive higher radiation during summer are precisely the ones that receive less radiation in winter, and vice versa. The idea of a compact form was to reduce the exposed surfaces to unwanted exchange of energy between interior and exterior. The cube was designed to fit in a 10-meter diameter circle to be built in any site of minimum 10 meters width, regardless of its orientation. In addition, other passive strategies were applied. The living spaces have daylight autonomy during the day almost all year. Natural ventilation is possible as a passive cooling strategy, taking advantage of winds and convection during certain periods of the year, the summer nights and the day in spring and autumn. Continuous thermal insulation prevents thermal bridges at the joints between different components of the shell. The efficient use of water was also a concern in this project. Therefore, it includes rainwater collection from the roof to use it for the toilets. The seasonal rain was considered to calculate the capacity of the rainwater storage tank. The living spaces were located to the north, while service spaces were located to south, and the stairs in the west facade work as a chamber to avoid the high solar radiation. Universal accessibility was resolved in ground floor, where there are all the indispensable spaces easily accessible by wheelchair. Here we can see a comparison between a conventional social house and our proposal. The graph shows the monthly heat gains over the line and the monthly heat losses under the line. In yellow, it is shown the large reduction in heat gains from solar radiation thanks to the implemented strategies. To achieve a comfortable indoor temperature the whole year, heat losses and heat gains must be balanced, equalizing them as a mirror. By compensating these differences, we can see the demands for heating and cooling. This graph shows the large reduction in these demands compared to a conventional social housing. The heating and cooling demands were reduced from 89 and 48 kilowatt-hour per square meter per year to only 22 and 10. This means a 75% reduction in energy demand. In this way, each house would consume around 500 cubic meter less gas and 1 megawatt hour less electricity per year. This annual saving in energy consumption is equivalent to 1% of the total construction cost of the house. Using only 4 photovoltaic panels and 1 solar thermal panel, it can be achieved a net zero energy building. This project demonstrates that sustainability is not necessarily complicated or expensive, but very simple, that it is possible to slash energy demands using easy application strategies without extra costs. As a result, the solar cube allows to reduce both, at the same time, the housing and energy deficits. There is a lot of work ahead. Thank you very much.